Can you see my screen? Cool. Okay. So, hi everyone. I'm going to present our work called Reconsidering Operating System Memory Optimizations in the Presence of Disaggregated Memory. This is a joint work between the ACSL lab at the Technion, Imperial College London, and the University of Edinburgh. Over time, the demand for additional memory in server increases. Data center applications exhibit larger and larger memory footprints. Well, RAM is expensive and is one of the leading contributors of overall data center expenses. However, there is a limit on how much RAM a single machine can accommodate due to the limited DIMM slots and CPU pins. Further, DIMM costs increase exponentially as its density increases. One approach to address this problem is by disaggregating memory from the compute blades. Instead of co-locating CPUs with large amounts of memory in a single blade, a disaggregated memory system introduces a memory blade. A memory blade has memory modules and is connected to the compute blades via an interconnect. Each compute blade has a small local DRAM memory and has access to the remote memory blade. Memory disaggregation enables to lower over-provisioning and independently scale compute and memory. Well, as we all know, there is no such thing as a free lunch. A drawback for disaggregated memory is the higher access latency to the memory blade. In the diagram below, we can see a continuum of access latencies to different memory technologies. Typical accesses to local DRAM has a latency of around 70 nanoseconds, and for persistent memory such as Optane, around 300 nanoseconds. Disaggregated memory, however, has a higher latency, expected to range between 750 nanoseconds and 1.5 microseconds with today's technologies. As I'll demonstrate in this presentation, when the remote memory access latency is in the disaggregated memory range, of certain system trade-offs change, which require a re-examination of typical memory subsystem optimizations. So in this work, we take a top-down approach in identifying and addressing these challenges and introduce Hotbox, our memory management subsystem for disaggregated memory systems. Some challenges we address are as follows. We first need to consider how we wish to access the disaggregated memory blade. Prior works have treated the blade either as a swap device, a directly accessible memory, or as a sort of a hybrid design between the two. Second, we observe that under the disaggregated memory latency regime, certain system trade-offs change. In particular, we note that typical page management optimizations break, such as huge pages and batching pages for migration. Further, we show that in a disaggregated memory system, the identification of which pages are hot matters most to performance, but the identification process itself is resource intensive. In this talk, I'll focus on the three challenges listed. First, I will address which model we chose for best performance in a disaggregated memory system. Next, we show that huge pages are actually ineffective in a disaggregated memory system and can actually hurt performance. Finally, I will address the issue of measuring a page's hotness with low overheads. So in this work, we utilize what we call the hybrid access model, which combines remote cache line accesses with page migrations. Further information and analysis is available in the paper, which is what led us to choose this access model. In the hybrid access model, every compute node has a small local memory and has access to a large remote memory. Both types of memory are directly addressable, but accesses to the remote memory incur high latency costs. Pages identified as hot in the disaggregated memory blade are migrated to the small local memory, and cold pages are migrated from the local memory to the remote. The choice of which pages are migrated are a part of the operating system's memory management policies. In our work, we re-examine the benefits of huge pages. In a traditional system, huge pages help reduce the translation costs incurred upon TLB miss, and they also increase the overall TLB reach. We ask whether huge pages are actually beneficial in a disaggregated memory system. We evaluate the impact that huge pages have on system performance by evaluating huge page-friendly workloads. We execute each workload with base and huge pages, and we place all of the page tables in local memory and the rest in remote memory, which has a higher latency than local memory. If we look at the graph, the y-axis of the graph depicts the speedups gained by using huge pages over base pages, and the x-axis is the access latency to the memory. At the small end of the latency spectrum, for example, local DRAM accesses and NUMA accesses, all workloads exhibit speedup. This kind of makes sense as huge page support for operating systems are designed for these latency regimes. As we increase our remote memory access latency, the benefits of huge pages start to diminish. Specifically, the benefits of huge pages under disaggregated memory latencies diminish altogether. As the access latencies increase, the relative overhead spent on address translation decreases. Therefore, the benefits of huge pages are not apparent when placed on disaggregated memory. To evaluate the impact of huge pages in local memory in a disaggregated memory system, we execute memcached serving Facebook's etc workload. As before, the y-axis depicts a speedup of huge pages execution versus base pages on local memory. The x-axis is the portion of the working set which can fit in the local memory. We place the hottest pages of the workload in local memory beforehand via offline analysis. As the portion of the local memory decreases, so does the speedup of the huge pages. At a certain point, we actually notice a slowdown of huge page execution versus base page execution. As there is a slowdown, and the performance didn't normalize to regular base page performance only, we investigated this issue further. We investigated first whether this is caused by memory bloat, which turned out not to be the case. We also asked ourselves whether the coarse granular information of huge pages affected our placement policy. But we statically place the hottest pages in local memory and do not migrate memory over time. Turns out that this slowdown occurs because the hot huge pages that reside in local memory contain cold base pages, which occupy valid local memory space. We call the phenomenon observed in the previous graph hotness fragmentation. Hotness fragmentation occurs when cold base pages reside within local huge pages. These huge pages are placed in local memory due to their overall hotness, and this phenomenon directly affects the performance. As a toy example, let's assume a disaggregated memory system with a local memory of 2 megabytes, which is the size of a huge page. Our toy workload has 512 base pages worth of hot data, each 4 kilobytes. When huge pages are enabled in local memory, the best case scenario is if all of the base pages are part of the same huge page, which is placed in local memory. However, in a typical scenario, these pages are not contiguous in the virtual address range and cannot be co-located together in the same huge page. This leads to an underutilization of precious local memory. In the disaggregated memory latency regime, placing hot pages in remote memory has a very high penalty. Consequently, it is much more efficient to have slightly worse translation performance to local memory than paying the high penalties for remote memory accesses. More information regarding hotness fragmentation and further details can be found in our paper. In order to classify pages as either hot or cold, we utilize the access bits in the page tables. Base pages provide finer hotness classification granularity, but the number of page table entries, which represent a virtual address range, is far larger than in a huge page-based system. This means that more system resources need to be spent when scanning a virtual address range backed by base pages as opposed to huge pages. Also, the access bit scanning frequency needs to be high enough in order to differentiate between hot and cold pages, and this obviously entails higher overheads, because if the scanning frequency is too low, all pages in the system will be classified as hot. At this point, we introduce Hotbox, our low-overhead OS memory subsystem for disaggregated memory systems, addressing the prior challenges introduced. Hotbox utilizes the hybrid memory access model to achieve high performance. It also uses the NUMA abstraction for local and remote memories. Hotbox uses base pages only to circumvent hotness fragmentation, as well as gain fine granular information on memory hotness. And finally, Hotbox employs an adaptive scanning and migration utility inspection to accurately classify page hotness, and to do so with low overheads. In the disaggregated memory latency regime, penalties for misidentification of hot pages are high. It is important to correctly classify pages in both local and remote memory. In the next slide, we'll go over the adaptive scanning and migration utility mechanisms. So Hotbox utilizes the adaptive scanning technique, which is similar to Linux's page frame reclaim mechanism, which differentiates between hot and cold pages, as well as to keep scanning overheads low. The diagram represents the migration and scanning mechanisms employed by Hotbox. On the right, we can see the active and inactive LRU lists for local memory. The left-hand side of the diagram represents the remote memory and Hotbox's classification technique for remote memory pages. Hotbox periodically scans pages which reside in remote memory and updates the state of them between cold, warm, and hot. Once a page is classified as hot in remote memory, it is unmapped from the page tables. Upon a subsequent access to the unmapped page, a page fault is raised, and the page is migrated to local memory on demand and inserted into the local memory's active list. This in turn increases the local memory pressure. Once the local memory pressure is raised, the active and inactive lists are shrinked by the operating system, and the pages at the bottom of the inactive list are examined and classified as either hot or cold. The adaptivity of the local memory scanning relies upon the presence of hot pages in the remote memory. So for example, if few hot pages are detected in remote memory, local memory scanning frequency is low and vice versa. However, once the hot pages or some hottest subset of them reside within the local memory, any further actions such as scanning and migration efforts are fruitless and will only hurt performance by exerting additional overheads onto our system. To control the remote memory scanning and the overall migration mechanism, Hotbox employs a migration utility inspection technique. The Hotbox utility monitor utilizes the CPU's performance counters, specifically the number of LLC misses to local and remote memory, to determine utility of the memory migrations it performs. The utility monitor inspects the local versus the remote memory miss ratios. If the local memory hit rate is not constant, either the migration mechanism is affecting the local memory hit ratio somehow, or the application itself is changing phases. So for example, the application is now loading a new data set, so we must resume and perform the memory scanning and migration in order to detect them in remote memory. Once the local hit ratio remains relatively constant, the migrations performed by Hotbox do not have any effect on the local memory hit rate. In that case, the utility monitor pauses the migration and scanning mechanisms in order to avoid scanning overheads and ineffective memory migrations. At this point, the system is essentially thrashing without performance gains from the migration operations. The utility monitor continues to inspect the LLC miss counters to detect any change in the state and resume migrations if necessary. So, we conduct our evaluation on Intel's PMAP hardware emulation platform. Now, this emulation platform actually enables us to configure an arbitrary access latency to a remote memory node. We evaluate a system where all the memory, apart from the page tables, reside within the remote memory node. Now, this serves as our lower bound on performance. We also evaluate a swap-based system that is optimized not to go via the block layer for additional performance. This is similar to fast swap from prior work. Nimble is the current state-of-the-art hybrid disaggregated memory system. We evaluate both Nimble with and without huge pages. And finally, we evaluate Hotbox with and without the adaptive throttling mechanism. In this graph, we compare the performance of the systems on two separate workloads, on Graph 500 and Memcached, which serves the Facebook's etc request pattern using the Mutilet client. The y-axis shows the speed up of the systems versus the all remote configuration. That is, all of the data is in the remote memory node and all accesses incur the higher latency. So in this graph, higher is actually better. The x-axis has the workloads, which is then divided into the local memory sizes relative to the working set size. And finally, each one of the bars is a different system that we have evaluated. So we can see from the highlighted bars that Hotbox outperforms the other systems. Specifically, we can see the effects of the adaptive throttling mechanism in Memcached. In this Memcached workload, it has a relatively static skew that doesn't change over time. Once the hot pages are correctly identified and placed in the local memory, the adaptive scanning mechanism pauses migrations, which lowers the scanning and migrations overhead, which has drastic effects on the overall system performance. If we compare Nimble with huge pages versus base pages in Graph 500, we observe that Nimble with base pages performs better than Nimble with huge pages. This is essentially a demonstration of the effects of hotness fragmentation in the Graph 500 workload for the Nimble system. Okay, sorry for the too detailed graph, but next we evaluate VoltDB TPCC for all of the systems. In this graph, the y-axis is actually the mean latency per request, so lower is better. The x-axis here depicts, first of all, the local memory size as a portion of the working set, and each cluster within the working size is a different remote memory access latency. So we have 750 nanoseconds, 1 micro, and 1.5 micro. Finally, each of the bars within each cluster is a different system that we have evaluated. Hotbox is currently on the right of each of the cluster of the bars. The colors or the colors in the breakdown for each one of the systems shows the contribution of overheads of each mechanism to the mean latency. So we have the current overheads that we have are the migration overheads, the local memory scanning overheads, the remote memory scanning overheads, and then what is left, the last part, is the application time. This is the actual time that the CPU runs the actual application itself without any of the system overheads. Hotbox overheads are substantially lower than all the other systems. Specifically, if we examine the non-colored portions of the bar, which is the actual application time, we see that it is really close to the native application. The native application time, by the way, in this graph is the bold line that runs across the graph. So we can see that in 750 nanoseconds, with a local memory size that can fit 40% of the working set size, excluding the overheads, Hotbox can achieve near native performance. That means all of the really hot pages are in local memory. So to conclude, in this presentation, we saw that disaggregated memory changes system design considerations and requires a re-examination of well-known memory optimizations. Specifically, we showed that huge pages actually hurt system performance. We also introduced Hotbox, a low-overhead memory subsystem for disaggregated memory. I would like to thank you all on this point. Thanks to the organizers. And are there any questions?
All right. Thank you for that great presentation. Let's all thank the speaker.
Thank you.
So we have, as before, a number of different ways of asking questions. Please feel free to post in Slack. You can also ask live virtually, or for people in the room, please feel free to walk up to the microphone here and ask a question in person. So while we're waiting for questions, I'm going to ask one. So you framed this work in the context of disaggregated memory, but do you think that these techniques would apply in other scenarios as well? For example, the panel mentioned NUMA as one potential challenge.
That's actually a very good question. Sorry, just mute here. That's actually a very good question. In the paper, we actually note and part of the presentation that many of our conclusions are specifically derived just towards disaggregated memory latencies. So, for example, we have observed that huge pages in that latency regime really actually hurt system performance, or at least do not improve system performance as they would do if the access latency was lower. So when we have evaluated our workloads in, let's say, a NUMA system or even on a non-volatile memory system, we actually noticed that huge pages have a much more beneficial effect. The same system, the same sayings could actually go for virtual machines, which use techniques that are akin to, let's say, 2D paging, where the delta of performance between huge pages and base pages is actually a bit bigger because it solves a bit more. I guess certain trade-offs exist, and there is a place towards, let's say, somehow incorporating the two together. But at this day and age, and currently, for disaggregated memory, huge pages actually bad performance.
Thanks. Yeah, sounds like there's lots of interesting additional research directions there. Any live questions? So I can ask another one.
Typical subpages and whatnot. There are works that actually try and tier memory at the language level. So, for example, there are works that utilize, let's say, memory allocators. And in the memory allocator, you can specify ahead of time whether this page is hot or not, is going to be hot or not, and the memory allocator will perform the tiering for you. So that could be a subpage. There is a paper called Semaru, which does language-specific hot memory tiering. But but if you want it potentially like transparent and to work with existing binaries and whatnot, I think it has to be at the level of the architecture.
Yeah, it makes sense. Well, I'm going to ask the third question, and then I think everyone can go to lunch. So the workloads you looked at, I think you looked at Graph 500 and basically benchmarks like that. In real-world systems, you oftentimes have very long-running workloads, very large heaps, kind of behavior that changes over time. Would that change anything for your approach?
That's again another good question. So essentially, we have run workloads which are also relatively long running. So for example, now Graph 500, we left it for a relatively long time and a lot of BFS iterations. But we did run a whole family of applications where the data sets rapidly change or relatively constant or have some sort of iterative access pattern. And we saw that with our migration detection mechanism, utility mechanism, it is actually able to capture that hot working set. And when, let's say, that working set is relatively stable for a specific period of time, we do not pay that price to detect that we just bring in stuff from the remote memory tier and it's not helping. So we pause migrations. But the second that something changes in the system, the application goes into a different phase where the local to remote memory ratio changes either for the better or for the worse. It doesn't matter. It indicates that there is a phase change within the application and possibly an opportunity in discovering even hotter pages, or the actual data set has shifted and we need to recapture the hot data set from the beginning. Yeah. Sorry, was I disconnected? Well, I guess I'm the host now.
Seems like the room actually disconnected. If I'm reading that right.
Okay, cool.
Thanks a lot. Thanks a lot.
Thank you. Thank you.
Right. Since the room seems to have troubles in connecting again, I guess we can already call it a break, right? And we'll be back in 2 hours after lunch. Thank you, everyone.